discuss with me is about the Big Bang. So let's go to a time closer to the Big Bang. Before I begin my talk on quantum information tools for the S-matrix bootstrap, so this is also going to be closer to the Big Bang. So let me see how many of you can recognize Professor Sinha in this photograph. Nope. Okay, so this is Professor Sinha, and this happens to be my father, and this is one of my uncles. Sadly, they're no longer there. So sometimes you will see him having this expression, and if you see him having this expression, this is what he's thinking. So before he starts thinking the same thing about me, let me just get on with my talk. So I will talk about the S-matrix bootstrap and how modern ideas are helping in reviving this ancient idea. So this is something that was pursued very actively from maybe around 1950s and 1960s, and this was called Jeffrey Chew's bootstrap program. And during Chew's time, one of the shortcomings was that powerful numerical methods weren't available. And that has been rectified because we have now powerful computers. We can revisit some of these old ideas. And so they said that I might talk about the conformal bootstrap, but my focus will be on the S-matrix bootstrap because this is a QCD community largely. So the recent success of the conformal bootstrap actually gives us motivation to look at the S-matrix bootstrap. So one of the successes for the conformal bootstrap, for example, has been the most accurate calculations numerically of the critical exponents of water. So this is something that I won't have time to explain. Rather, what I will focus on is what is the S-matrix bootstrap, which essentially just uses unitarity and crossing symmetry as its inputs, and tries to ask the following question: that is there a unique theory that describes nature? So this is a very fanciful and very sort of ambitious question. So this was the question that was asked in the 1950s. I will tell you a little bit about the history. And what happens is that when you explore things numerically with the current numerical techniques, you get a space of allowed theories. So you will see this space of allowed theories frequently in my talk. So this is a space of allowed theories describing pion scattering. So pion scattering in the QCD framework. So there will be some x-axis. So in this particular case, it will be an x-axis labeled by what is called an Adler zero, and a y-axis which is labeled by another Adler zero. And the blue region is going to be an allowed space of S matrices, which can potentially describe pion scattering. So one of the massive goals in this bootstrap program was that we don't want to talk in a Lagrangian framework because we don't want to calculate finite diagrams. So we don't want to talk perturbatively, we don't want to expand perturbatively and encounter infinities, we want to just work with observables directly. So then the question that you should ask is that if you don't have a Lagrangian, then how do we know, how do we select good theories? So of course you can always go and compare with experiments and say that this is a good theory, it matches with experiments, I'm going to use this. But without actually appealing to experimental results, how do you know that you have a good theory? So I will take some inspiration from recent developments in quantum information theory and ask whether there's a selection principle in the space of S matrices that says that the QCD point or the standard model point is special. And this is a fertile play area, so this is something that is evolving. This is probably just 5 or 6 years old, so there's a lot of things that you can explore in this area. So this is based on a few papers that I've been writing over the last few years. I should say that my talk is largely going to be based on these two papers on Jishnu Bose and Pritish Sinan, the Shashwat Tiwari were undergraduate students working with me in IISc, and Parthiv Vada was my graduate student. And there's some ongoing work as well. I won't have too much time to explain the technical details of this paper. This is a very, very smart PhD student that I have, Ahmadullah Zahid. CSDR stands for Crossing Symmetric Dispersion Relations. This is published in PRL, so I will briefly refer to it once. And towards the end, right in the end, I'm going to throw out a speculative idea that I've been recently working on, which connects this crossing symmetric dispersion relation with an area of mathematics called knot theory. So let's get going with bootstrapping quantum field theories. So I should say that if you find the talk technical and if you get lost, do stop me and ask questions. I would encourage that rather than actually losing you halfway through my talk. So here is the history. So the idea of S matrix was first proposed by John Wheeler in a paper in 1937. And it's very curious that this was the idea of what eventually came to be known as the S matrix bootstrap was historically proposed in a couple of papers by Heisenberg during the wartime. These couple of papers were written where supposedly Heisenberg was supposed to be working on the bomb for Germany. And of course, it became a very active framework that was pursued by Jeffrey Chew. So there's a review that he wrote in 1964 called The Search for the S Matrix Axioms. This is available on Inspired Web. It's a very inspiring piece of work. I would encourage you to read it. So the S matrix bootstrap, as you know, was largely abandoned because QCD was discovered. It was calculationally very powerful. You could predict a lot of things. You could predict new particles. So the outcomes of the S matrix bootstrap was the invention of string theory, which Sunil actually referred to. So I will actually show you some interesting plots about how string theory was invented. And it was largely abandoned. Now, only recently, maybe over the last 5 or 6 years, has it again come back because people have now powerful numerical techniques to explore this idea once again. So the idea of the S matrix was introduced by Wheeler in 1937, and it was actively pursued in the 1960s by Landau, Chew, Mandelstam, Lehman, Martin, and then the Cambridge folks, Eden, Olive, Polkinghorne, Lanshaw. And it relies on a very basic set of principles like Lorentz invariance, unitarity, and analyticity. And crossing symmetry. Crossing symmetry plays a major role. And the question is that are these principles constraining enough to give you a unique S matrix to describe at least pion scattering? So it's a well-defined question. And we want to do it in a Lagrangian-free approach, so we don't want to talk about the Lagrangian at all. So as I told you, a favorite problem that people used to study at that point of time in the 1950s was pion scattering. So you can actually experimentally measure a lot of things about pions. You can measure what are called scattering lengths and effective ranges. So if you open this very famous review, you will see that there are models and then there are experimental results here, which you can try to match up. Whatever. So these are all models in different guises which come from chiral perturbation theory. Then as you saw this famous plot, so one of the things that you learn from pions is that if you plot the spin versus m squared is the real part of the resonance masses, they appear to lie on a straight line. And in fact, you can do a fit, you can get a linear slope and as well as a correction. And the correction phenomenologically appears to be positive, so it's convex. So one of the challenges is if your model can actually predict that it's going to be convex. And this famous behavior is called the Reger behavior. It gave rise to string theory. So this is something that you want to see. You want to be able to produce this experimental data from your bootstrap analysis. So let me just set up some the framework. So we are going to discuss 2-to-2 scattering. It's the simplest scattering problem in quantum field theory. We're going to discuss scalar scattering. So we're going to use Mandelstam variables, and the angle is related to the Mandelstam variables in this way. S and T are Mandelstam variables. And scattering lengths. So when you do a partial wave expansion in terms of these Mandelstam variables, the scattering length is given as the leading Taylor expansion coefficient of the partial wave coefficient. And the second Taylor expansion coefficient is what is called the effective range. And these two things are in principle experimentally measurable, although the effective range is not experimentally well known so far. So the basic idea of string of the S-matrix bootstrap is to use a crossing symmetric basis and just check unitarity. And surprisingly, these conditions can be recast into a semi-definite programming problem. So that is the key insight that has happened over the last several years. This is a new tool, numerical tool that has come to the market, which enables us to analyze both the conformal bootstrap as well as the S-matrix bootstrap. So this is something that was not available in the 1950s, but this is something that we can readily use clusters, or if you have more powerful resources, you can just use a supercomputer to analyze. So what are the things that we will somehow, during my conversion to PDF, some of the things have been missed, but anyway, it's not very important. So we are going to use some very basic inputs. So you have to give some inputs when you're talking about the S-matrix bootstrap. So one thing is that we are going to use unitarity, we are going to use crossing symmetry, but what else? So you have to tell that there is going to be some bounds on the scattering length. These actually follow from dispersion relations. Okay, so we are going to impose those scattering length bounds. Then we are going to impose just one experimental data, that we have the row resonance. We're going to take that as an input. We'll just use the fact that there's a row resonance in the model. Okay? So the question that we can use is that, using this, can we get the scattering lengths to experimentally agree? Do we see Regge behavior? And do we see some special geometric property in the space of allowed theories? And more interestingly is, what is so special about these S matrices that we get? Okay. So let's start benchmarking the space of allowed theories. So as I told you that there are going to be two parameters that I can dial, which are called Adler zeros. So it's not important for you to know what they are, but these are things that I can dial. And so I know that there is chiral perturbation theory, which is supposed to describe, it's an approximation to the pion scattering problem. So the chiral perturbation theory values lie here on the plane of the Adler zeros. So the black one is the tree-level chiral perturbation theory value, which was calculated by Weinberg a long time back. The orange one is the one-loop one, and the red is the two-loop one. Two-loop is the state of the art. Nobody has done beyond two loops in chiral perturbation theory. So on this plane of Adler zeros, these are the known theories that lie. Then we can do something interesting. You can actually also plot on the plane of Adler zeros an ancient model, which was a precursor to string theory, which is called the Laplace Trapezoid model. So it looks very similar to the string model, so it will look like a beta function, except that it is a non-unitary theory, so that is why we don't talk about it. But you can, of course, make these models, which look like these Laplace Trapezoid models, and they lie on a straight line on the plane of Adler zero. The thing to note is that these Laplace Trapezoid models pass very close by to these chiral perturbation theory values. But of course, this line is a set of S matrices which are non-unitary. So in that sense, they are not terribly interesting. The more interesting thing is, what do you get when you actually put in your optimization problem, you put in the semi-definite programming problem, you use unitarity, you use crossing symmetry, and you ask, what are the space of allowed S matrices that I get from the S matrix bootstrap? So the space of S matrices is what we can call the river. So the blue region is any S matrix that lies within the blue region is an allowed S matrix. Okay. The thing to note is that, first of all, this line of this Laplace Trapezoid model just about misses. If you zoom in, you will see that it just about misses being within the river, which is good. Because after all, the Laplace Trapezoid model is supposed to be non-unitary, so it should not lie in the space of allowed theories. On the other hand, you can see that these chiral perturbation theory values actually lie very close to the boundary of the space of allowed S matrices, which essentially is telling us that the boundary is the unitarization of the Laplace Trapezoid models. Okay? It's a different issue whether we can actually locate the theory that sort of will tell us that this is whatever you want to call it, whether it's a string theory or whether it's something else, or we don't know. But it's at least there are a bunch of S matrices which have unitarized the Laplace Trapezoid model. And so this red cross is what we will call the QCD point. Okay? Now, see, as you can see that there are some peculiar features about this. So there are some interesting turning points, if you want to call them, or kinks in the space of allowed S matrices. One of them happens close to this sort of region where the QCD point sits. Then there is some peakish feature here, and then there is another feature which actually there's a turning over here that happens. So these are going to be interesting things, because what happens, or what we found, is that only in this neighborhood do you get Reget behavior. So if you plot the resonances, you get them to lie on a straight line. So you could say that, okay, maybe the QCD point could be one of these S matrices that is lying here, or it could also be one of the S matrices that are lying here. So this is what I meant, that you only get Reget behavior near the kinks. And another very interesting thing that happens is that those of you who have opened the particle data group, the PDG handbook, and you see what are the resonances that actually lie on the pion scattering Reget trajectory, you will see that there's a scalar meson, which is called the F0 meson, which is highly controversial. It has got large error bars. So the S matrix bootstrap actually predicts where the F0 meson is supposed to lie, and gives you error bars for that as well. And it agrees very well with the analysis that was carried out by Pelaez in 2015. So now comes the main question. Suppose I asked you, I want to find out how close my theory is, my S matrix is, to say chiral perturbation theory. And you're going to say, look at the plot and say, okay, and let me take a ruler and measure what is the distance. But that is crazy. That is not what I mean by how close it is. So what tool do I use? So how do I answer this question? How close two theories are in theory space? So this is what we use. So this is one of the modern lessons that we have learned from quantum information theory, is that we can use something called relative entropy. So what is relative entropy? So the relative entropy D of two density matrices, ρ1 and ρ2, is defined like so. So this was, you can find reviews by Vedral, and there's a nice review by Edward Beaton from 2018, which tells you what the meaning of this relative entropy is. So we can take one density matrix from chiral perturbation theory, and the other one along the boundary, and then try to get as close as possible, or try to minimize this distance in theory space. So mathematically what you do is that you take the initial state, which will be two states, two pion states, final state, which will be again two pion states, and you project so that you pretend that there's a detector that is sitting in some angular region centered around some value of theta, and then this is the projection operator, which is like a detector which is detecting those particles. And you can construct a density matrix, and using this density matrix you can go ahead and calculate the relative entropy. There are some intermediate steps in the calculation which are sort of, so for example, you can calculate, once you get a density matrix, you can calculate the entanglement entropy by calculating the von Neumann entropy for the reduced density matrix. That appears to be divergent, so that is not a very good measure. What you need to do is relative entropy, which is finite. And when you do that, you get some formula which is in terms of the amplitude square. That is what, as theorists, what you calculate are probabilities of scattering happening, and that is exactly what you see in these formulas. So you can go ahead and plot this, and you can ask mathematically which is the theory that is closest to this chiral perturbation theory. So this is what is called hypothesis testing, that if you have two competing theories, T1 and T2, which give two different probability densities, then how do you know whether they are the same theories? Can you quantify that? So you use this thing called the relative entropy. So if you make n measurements, then the confidence with which you can say that these two theories are different is given by this formula. So if B is very large, then the confidence goes down as you expect. So that's the reason why this relative entropy is a good thing to use. So the larger relative entropy means that you will take fewer number of measurements. And using that, we set some kind of a cutoff, and then you can see that there are a large number of S matrices which are lying on the boundary, which can be said to be closest to chiral perturbation theory. But that, of course, depends on what value of energy you're using. So if you are focusing on low energies, then all these theories would be a good approximation to the chiral perturbation theory answer. So now the question comes, so what is so special about this red point, which is supposed to be the chiral perturbation theory value or the QCD value? So we go back to the ancient literature to see if there is some insight to be had from there. And so we look at a paper by Mandelstam in 1974, and the hint lies there. See, he says the narrow resonance approximation may be regarded as a kind of a weak coupling approximation. If resonances are narrow, all decay times are long and all scattering amplitudes are small. So you expect to see some minimization of the scattering amplitude if it is to mimic something that is close to this narrow resonance approximation. And that is precisely what happens. You actually see a sharp minimization of the scattering amplitude precisely at this point. There's another fancier way of quantifying this. You can actually measure how much entanglement there is in the final state pions. Because if your state is very entangled, you would have thought that effective field theory description will be difficult. Okay? So effective field theory intuition tells us that the final state entanglement should be reduced if your effective field theory is a valid description. And that is also something, sorry. That is also something that happens. You actually see a sharp drop in what a quantity called entanglement power near the QCD point. I'm not saying that, okay, so I have finally found a selection principle which is going to tell you non-perturbatively how to select out the QCD S matrix from S matrix bootstrap. I'm saying that these are quite suggestive, that there are principles like these at play. Because after all, you don't have a Lagrangian mechanism. You can't talk about equations of motion. So what do you talk about? Oh, sorry. So you can plot the entanglement power. As you can see that it does have this minimization close to this QCD point. So this actually sort of tells you that maybe there is some principle